Welcome to the Waves and Sound lesson on standing waves on a string. This video starts a series of videos on standing waves and instruments, and as mentioned, we're going to start by taking a look at standing waves on string instruments. Before we begin our discussion with standing waves on a string, we first need to understand what a standing wave is, how it's formed, and to do that we're going to take a look at a neat simulation. Okay, here we are at the simulation, and what we're going to do is we're going to take a look at sending energy through a medium and what happens to that energy when it hits a fixed end, and then we'll proceed from there. Over here to the right we have our medium, which is a series of beads, it looks like, and it's attached to a clamp and is held fixed at that end. On the left hand end we have an oscillator that's going to simply raise up and down and create energy in our medium, which is going to then transfer from one end to the other. To start off with here, I'm just going to send a single pulse, and what I want you to observe is what happens to the pulse when it hits that fixed end on the right hand side. As you can see, as it hits the fixed end on the right hand side, it goes down the medium as a crest, but then reflects, inverts, and comes back as a trough. The oscillator is not continuing to move, so it then acts as a fixed end as well, and the trough moves to the left, hits the fixed end, inverts, and goes back to the right as a crest. Okay? Now if I time it just right, I sent another crest to the right while the trough was coming to the left. And what's happening here is that as the energy is passing through each other, we get some constructive and destructive interference happening during that. And I'm going to pause that right now, and we're going to step this a little bit at a time. And you can see the crest that's moving to the right is about to pass through the trough that's moving to the left. And now the crest is continuing to the right as the trough is moving to the left. Both are going to hit their fixed ends, invert, and continue to come back. Okay? Now, the reason I'm showing you this is because this is how standing waves in a string are formed. This is how standing waves in any medium are formed. As I'm now going to turn the oscillator on by itself, and it's just going to continuously form waves that travel through the string, what's going to happen is these waves hit the fixed end, invert, and then start to interfere with each other. The waves have to be equal amplitude, which they will be. They have to be equal wavelength at the same frequency, traveling through the same medium, which they are. They're always traveling through this particular string of beads here. And they have to be traveling in opposite directions, which they do because they hit the fixed end and reflect off of that fixed end. Those are the conditions for a standing wave, and let me go ahead and get that going here for you. What I want you to especially note are the green beads, and how at certain times the green beads won't be moving at all. So I'm going to continue to show this, and in a moment here when the green beads are motionless, here's our standing wave. You can see what's happening if we take this red region right here. This red region is simply oscillating back and forth across the equilibrium position while the green spots remain fixed. Well, these oscillating red areas we would call an antinode, and the fixed green regions we would call nodes. The standing wave wavelength is still a complete crest and trough, but you can see that would require two antinodes to make up one wavelength. I'm going to start this back up again, and you can watch this as it continues. It gets a little nutty after a while, so it's kind of neat to restart it to watch it. And right there we have a standing wave formed. Okay, again, this would be an antinode here. This is an antinode here. And does it look like an antinode right now in fixed time? But as the red region oscillates back and forth, kind of pausing it and restarting it there for you, that's what makes up an antinode. All right, we're going to go back to our diagram here and talk more specifically about standing waves on a string and the relationship between the length of the string, the wavelength, and the frequencies that are produced in that string. Okay, just to review from our previous simulation, the diagram I'm about to draw, this dotted line represents the equilibrium position. One standing wave would be a crest and a trough that flips and inverts. Trough becomes crest, crest becomes trough. And so that would be what one complete standing wave would look like. These two regions here are called antinodes, and these regions here, here, and here are called nodes. Antinodes are areas of constructive interference, while nodes are areas of destructive interference. Okay? All right. Now as we take a look at this in strings, what you need to do on in your notebook, and your notebook has lines on it, is give yourself 3 equally length dashed lines here. So in our comparison, the length, which we use the symbol L, for each of our strings is L. And what we want to take a look at is what is, first of all, how much of a standing wave fits in each of these lengths for the various frequencies that can be produced in this length of string. The first frequency we're going to take a look at is called F1. It is the lowest frequency note that can be produced in a string, and that is why it is called the fundamental frequency. Now, looking at our standing wave, our complete standing wave, we note that each end on our stringed instrument, let's just say it's a guitar, for example, one end of the string is fixed, the other end of the string is fixed. What that means is a node is required to exist whenever we have a fixed end. So, what's the smallest part of the standing wave you see at the top, drawn at the top, that will fit in this length L, that will meet the requirements to have a node at both ends? I'll say that again. What's the smallest part of a standing wave that can fit in this length L and have a node at both ends? Well, if you examine carefully, that means we would have only one antinode, so one crest, which flips and inverts and becomes a trough. Well, how much of a standing wave is that? That's a half a standing wave. So length L produced half a wavelength. Now, we're going to go down here at the bottom as well and talk about each of these as we go. So for F1, the fundamental frequency, V equals F1 lambda. Well, if we solve lambda in terms of L, lambda would equal 2 times L. So V, the speed in the string, equals F1, the fundamental frequency, times 2L. That is a relationship shown with a wave equation between the speed, the frequency, the wavelength, and the length of the string. All right? Now let's go ahead and take a look at F2. What's the next largest? By the way, up at F1, how would you get this note? You would simply take the guitar string and pluck it. It would vibrate back and forth, a note at each end, and that's how you get the lowest frequency note produced on that string. Now let's take a look at F2. F2 is called the second harmonic. What is the next largest standing wave that can be produced on this same length of string, meeting the conditions that you have to have a fixed end on the left, a fixed end on the right, yet produce a standing wave in a string? Well, that would be if we now put a node also in the middle. By the way, how we would do that on a string instrument, we would put our finger there. So what does that do? We now vibrate the string, and that would cause a crest to now invert and become a trough, to now invert and become a crest, which now inverts and becomes a trough. Well, how much of a standing wave is that? Clearly, as you can see, it matches the diagram above. So in this length L, we've produced one wavelength standing wave. Again, down below, let's take a look at the relationships here. For the second harmonic, F2, let's start off with V equals F2 lambda. Again, what's lambda in terms of L? V equals F2 times L. Now we can also see a relationship between F2 and F1. The speed of the sound in both medium and both strings is identical. So we could set these two to each other, set these two equations, V equals F1 to L equal to F2L, and solve for F2 in terms of F1. L's cancel, and you can see that F2 equals 2 F1. That means the second harmonic is double the frequency of the fundamental frequency. And in music, we call that an octave. All right, we need to wrap this up and talk about the third harmonic. We have to have a node on each the left and right end, yet still produce some kind of standing wave in between. What's the next largest standing wave that can be produced here? Well, that would be if we took and put our finger 1/3 from the end, either end, and that would create crest, then trough, then crest, invert, trough, crest, trough. L equals 3/2 lambda. You can clearly see it. That's 1.5 wavelengths. So for the third harmonic, V equals F3 lambda. V equals F3. Now in terms of L, 2/3 L. To get lambda over here, we multiply both sides by 2/3, so it's going to be 2/3 L. Now compare that to the original. Now compare that equation to the first one, and you would get F3 in terms of the fundamental frequency would be 3 F1. So the third harmonic is triple the fundamental frequency. If you have any questions on any of this, feel free to ask in class. And this wraps up our discussion on standing waves on a string.